Hello and welcome to Biological and Physical Chemistry, topic 1.3. This lecture will be talking about carboxylic acids and the derivatives of carboxylic acids. So a carboxylic acid is a carbonyl with an extra O minus or an OH coming off it, and an R group, so some sort of carbon chain. So an overview of the lecture, we're going to talk about physical properties of carboxylic acids, acidity and effects of substitution. We're going to talk about the solubility of carboxylic acids. We're going to talk about preparation of carboxylic acids, the hydrolysis of esters and saponification, and also from Grignards and oxidation of alcohols. We're going to talk about ester and esterification, lipids and amphiphthalic molecules, acid chlorides and anhydrides, reactivity of the carboxylic acid derivatives and the substitution reactions, and polymers. Okay, so carboxylic acids and derivatives. So carboxylic acids, like I said, have a carbonyl and an OH coming off the carbonyl carbon, and then it has an R group. Okay, so examples of carboxylic acids and esters are oxalic acid, which is found in spinach and rhubarb, acetic acid, which is vinegar, citric acid, which is found in fruit, ascorbic acid, which is vitamin C, which is also found in fruit and great for your skin, ibuprofen and aspirin. So the carbon is sp2 hybridized and hydrogen bonding occurs from the carboxylic acid. So here we have our carbon, our carbonyl with our oxygen, and then from that carbon we have our oxygen and our hydrogen, and we've got hydrogen bonding between that OH and the carbonyl oxygen of another carboxylic acid that's close by. Okay, so this is our hydrogen bonding between the carbonyl groups. Okay, they're weakly acidic, so their pKa's are between 1.8 and 4.8. So remember, pKa is the measure of how strong a weak acid is. So the smaller the pKa, the stronger the acid. So it's the same as pH, so the smaller the pH, the stronger the acid. pKa's are talking about only weak acids. So the smaller the pKa, the stronger the weak acid. Okay, and in the nomenclature, the carboxylic acids are the higher priority. Okay, so looking at nomenclature of this particular carboxylic acid, we have our carboxylic acid here, we have an alcohol, and we have an ether. Okay, so we call it 1, 2, 3, 4. Carboxylic acid is the biggest, so it's butanoic acid. We've got a 3-hydroxy and a 4-methoxy. So the methyl group's coming off the oxy. So the interesting thing about carboxylic acids is they have resonance stabilization. So looking at this structure here, we have our carboxylic acid. We can have the lone pairs kick in, and we can have the bonding pair kick up onto the oxygen. So we have an anion and a cation in the same molecule. Okay, so these two structures are equivalent, so they contribute to the stability of the carboxylic acid moiety. Okay, and then if you have the proton transfer from here to here, okay, so transferring over, then you would have the carboxylic acid again. So carboxylic acids and the derivatives, so just a refresher on the different derivatives that you can get from carboxylic acids. So you may have seen these in the past. Some of them were mentioned in Chemistry for Living Systems, just to the point of this is this. We didn't really go into chemistry. So we've got carboxylic acids, again, which is the carbonyl with an OH, and the suffix on that is oic acid with your naming. We've got anhydrides, So when they're symmetrical, you can just call it an anhydride. When they're unsymmetrical, then you have to do it alphabetically. Okay, so you've got your carbonyl oxygen, and then you've got an oxygen linking the two carbonyls. Okay, so you've got a carbon with an oxygen, so carbonyl, we've got our oxygen linking it to another carbonyl. Okay, so that's our anhydrides. So you can see here the two R groups are the same, and here with our unsymmetrical one we've got R and R prime. So we've got two different R groups. We've got acid chlorides, or we've got acid chlorides. So we've got a carbonyl with a halogen, so a chlorine group, and that's oil halide. So usually they're chlorides. We've got our esters, which we've kind of talked about but not really talked about. So we've got our carbonyl, we've got our oxygen, and then we've got two R groups. Okay, and they can be the same or different. So the prefix comes from what's on the OH side, and the suffix comes from what's on the carbon side. And we have OH at the end. So we have thiol esters, so same deal with the nomenclature, but instead of OH we call it thiolate. Okay, so thiol is when we have a sulfur instead of the oxygen there. We have amides, so an amide is a carbonyl with a nitrogen, and we have nitriles. Okay, so carbon triple bond to an N, so a nitrile. We'll talk more about our nitrogen containing compounds in topic 1.5. Okay, so let's have a look at the physical properties, so the boiling points and solubility. So it's dependent again on the chain length and the even odd carbon numbering and branching. So let's have a look here. So we have our carboxylic acid, so our formic acid, which is a carboxylic acid with a hydrogen. Okay, so carboxylic acid with a hydrogen, so formic acid or methanoic acid if you're going to use the IUPAC naming. We've got ethanoic, so bringing in a carbon, coming off the carbonyl. Then we have propanoic acid, butanoic, pentanoic, hexanoic, heptanoic, octanoic, nonanoic, and decanoic acid. Okay, so going up to 10 carbon chain there. So have a look at our boiling point. Our boiling point is getting very high when we have our 10 carbon chain compared to when we just have our 1 carbon chain. So the longer the carbon chain, the higher the boiling point. Okay, so melting points do not depend on the chain length. You can see that there's a irregular pattern here. So unbranched acids with even number of carbons have higher melting points than their odd numbered equivalents. Okay, and that's got to do with the intermolecular attractive forces in the solid state. We've got even numbered acids can interact more strongly, and formic and acetic acids have particularly high melting points, reflecting the importance of hydrogen bonding for these acids. Okay, so formic acid and acetic acid have fairly high melting points. So that's got to do with that hydrogen bonding that can occur with a simpler molecule. So just going back here and showing you the hydrogen bonding that we're talking about. So we've got a lot of this happening with the really small methanoic and ethanoic acid. So acidity. So let's have a look at the acidity. So we've got our carboxylic acid. When it's in water, you get the carboxylate anion, and you get your H3O+. So compared to an alkoxide, which we've talked about in the past, the carboxylate anion is resonance stabilized. So the equilibrium lies really far on this right-hand side. So the carboxylate anion is in favor. So the resonance stabilization that we're talking about is we can have our carboxylate like this, okay, with our negative on one of the oxygen and a double bond on the other, or we can have it the other way around. So we've got resonance stabilization, and we generally draw it as a dashed line with the negative shared over those two to indicate that delocalization of those electrons and the real stability that you find in that carboxylate. So with an alkoxide that we've talked about in the past, there's no resonance stabilization because that negative charge can only go on that oxygen. It's not going to get passed onto one of the carbons that are surrounding it. So our carboxylate is a lot more stable, so the equilibrium lies towards the formation of the carboxylate anion. Okay, so the relative stability of the conjugate base, okay, so this carboxylate anion, makes acids more acidic. So the pKa's are usually between 1.8 and 4.8. So again, remember, the smaller the pKa, the stronger the acid. So let's have a look at this table here. So we've got hydrochloric acid, which is a strong acid, has a pKa of -7. Okay, so generally you don't talk about pKa with strong acids, it's only for the weak ones. It's a way of talking about weak acids. We have our trichloroacetic acid, which is at 0.7. We have our dichloroacetic acid, which is 1.5, and our chloroacetic acid, which is at 2.8. And our normal acetic acid, without any chlorines on it, at 4.8. So we can see that by introducing those chlorine groups, we're making it a stronger base, By introducing those chlorine groups, we're making it a stronger acid, so it's got a lower pKa, and that's because the conjugate base is more stable. And we'll talk a little bit more about how adding chlorine groups are going to affect this. So if we've got one chlorine group versus 3 chlorine groups. So we'll talk about this a little bit later. So remember, we've talked about buffers in the past, and you actually did the experiment with this phosphoric acid, so our triprotic acid, back in Chemistry for Living Systems. So again, we titrated it with a strong base, sodium hydroxide, and we checked the pH after we added certain amounts of the sodium hydroxide. So generally in the lab we got probably to about here, our second equivalence point, and we didn't really see the third one because we didn't do it for long enough. So you can see what we've got here on the titration curve. Just to refresh you, we have our buffer region. Okay, so you're adding in a lot of base, but the pH isn't changing much, so we've got like a sort of a flat piece in the curve, and that's because it's resisting change to pH. Once you've saturated that buffering capacity, you will have a sharp increase in pH, and halfway through that sharp increase is your first equivalence point. And then you have your second buffer region, sharp increase, second equivalence point, third buffer region, and third equivalence point. Okay, so the buffering occurs most effectively ±1 of the pKa. So the pKa, remember, is equal to the pH at your midpoint. So your half equivalence point, so halfway through your buffering region is your midpoint, and going across to our pH, that will tell you that your pKa for this first association, so the first proton, would be around 2.1. Okay, and then for the second proton from our triprotic acid would be around 5.2, and then our third one would be around 8 or 9. Okay. So remember back to your Henderson-Hasselbalch equation. So when your weak acid and conjugate base are equal, then you're at the equivalence point where your pH equals your pKa. So getting back to how substituents affect the acidity. So again, remember, the lower the pKa, the stronger the weak acid. So the pKa can be affected by what groups attached to it. So if we have electron withdrawing groups, so groups that pull electrons away from that carboxylate anion and stabilizes that anion by pulling the negativity away, making this more positive. Okay. So if we've stabilized this carboxylate anion, we decrease the pKa and therefore make it more acidic. So how can we stabilize this carboxylate anion? We want to attach electronegative groups to the molecule. Okay, so the closer the electronegative group is to that carbonyl carbon, so this carbon here that's got the carboxylate on it, the more delta positive it would be, so the more this is stabilized. So let's have a look here. So we've got pKa, so just the normal, what have we got? Methylpropanoic acid. So just normal butanoic acid comes at a pKa of 4.9. If we add a chlorine to it at the very end, it drops down to about 4.5, so it's getting a little bit more acidic because we've got that pull of electrons away from the carboxylate anion. If the chlorine comes a bit closer, it becomes more acidic, and if it's right next to it, it's down at 2.8, so it's directly pulling electrons, and it's close enough to have a substantial effect. Okay, so the closer the electron withdrawing group is attached to the carboxylate anion, the more acidic the compound is, so the lower the pKa. So just a refresher on your neutralization reaction. So whenever you have an acid and a base and you mix them together, they neutralize, so going to a pH around about 7, and you'll form a salt and water. So benzoic acid, our carboxylic acid, benzoic acid, is mixed with sodium hydroxide, and we make sodium benzoate and water. Okay, so charged species are more soluble. We've talked about this a couple of times in the other lectures, but this one is another place where we can reinforce this learning objective. So reacting propanoic acid with a base, such as sodium hydrogen carbonate, so a nice weak base there, it increases the solubility of the acid. Okay, so it increases the solubility by forming charged species, so the salt. So we've got our propanoic acid, we've got our sodium hydrogen carbonate, we then have our carboxylate anion, which is stabilized by the sodium, and we have carbon dioxide and water being produced. So you can see we've got this carbon dioxide gas being produced, so we would have bubbles. So when you dissolve your Barocca and aspirate clear and you get those bubbles, we've got our acid mixing with base. When it's in an aqueous environment, it forms the charged species. Okay, so similar to this, and we have the bubbles. So amines can also be used in a similar way, forming ammonium salts. Okay, and we'll talk a little bit more about our nitrogens in topic 1.5. And all these salt-forming reactions are useful in the pharmaceutical industry for solubilizing drugs to make them more easily administered, such as Barocca and aspirate clear. Okay, so let's have a look at esters. So remember, an ester is your carbonyl with your O and a carbon group coming off it. So esters generally smell really nice. So found in fruits, flowers, and flavors. The nomenclature, so you derive one group from the alcohol and the other group is with the O8. So the smaller priority group is your alcohol and your higher priority group is your O8. So in this case we've got meth-eth. Okay, so we've got an ethyl and we've got meth-eth-prop-but, so we've got butanoate. So we've got ethyl butanoate. So that NO8 takes into account that whole ester group that's in there. Okay, so we don't need to re-say this oxygen. So here are some esters. You may have made them in high school, in the lab. They generally work okay if the reaction, you have the right ratios of your alcohol and your acid to start with, so you don't have too much excess of your acid. Otherwise it just smells like vinegar. So you could have your ethyl methanoate, so ethyl methanoate, which is your rum flavour. You've got your raspberry, banana, orange, jasmine, apple, pineapple, pear or apricot, and your marzipan. Okay, and you can see the nomenclature there is, as we talked about before. So we've got our octyl, and then we've got our the acetate is a bit general, but it'll be meth, eth, and O8. Okay, so acetate's not really our UPAC nomenclature there. So let's look at our acid halides and our acid anhydrides. Okay, so our acid anhydrides, like we said before, an anhydride is a carbonyl connected via an oxygen to another carbonyl. And then we've got our acid halides, which is a carbonyl with a halogen. Okay, so your acid chlorides are the most common acid halides. So your acid anhydride, we've got two acetyl groups linked by an oxygen. The formation is from a carboxylic acid and a acid halide. Okay, and that's how we make our acid anhydrides. They can be symmetrical, unsymmetrical, or cyclic. So here's an example of a cyclic one. Okay, another cyclic one. Okay, and looking at our acid halides, we've got one acetyl group bonded to a halogen. Sorry, it's made with thionyl chloride and a carboxylic acid. Okay, so this reaction we have talked about before. Okay, so remember converting alcohols to alkyl halides. And then we have our alkyl halide. In this case it would have to be the chloride because we've done the chloride in the reaction there. Okay. Okay, so we're going to talk about the reactivity of carboxylic acids and their derivatives. So first of all, how do we prepare carboxylic acids? So carboxylic acids, like we've talked about before, can be prepared from primary alcohols. So primary alcohols, examples include ethanol and propan-1-ol. And we can do these using oxidation reactions. So using really strong oxidizing agents and pushing it all the way from your alcohol to your carboxylic acid. Okay, so remember your strong oxidizing agents we've talked about in topic 1.2. So we've got our potassium dichromate and our potassium permanganate. Okay, so we've gone from an alcohol all the way to our carboxylic acid. Or we've gone from a alkane all the way to the carboxylic acid. Okay, so acetic acid is produced commercially, so on large scales. It's more economical to form your acetic acid from methanol and carbon monoxide with a rhodium catalyst. Okay, so in industry it's done a little bit differently. So other ways, again, our Grignard reagents, which we've talked about in topic 1.2. So remember, your Grignard reagent turns some sort of carbon group into a carbanion, so a negatively charged carbon. So instead of having this MgBi, okay, so on this benzene ring you've essentially got a minus on this carbon here. And then you bubble it with dry ice, and then you get your carboxylate. And then if you quench the reaction, you can make your carboxylic acid. So again, the mechanism, so you got your negatively charged R group attacks your carbonyl carbon, which is your only carbon in dry ice, so CO2, and then you attach that. Okay, so you've got your one carbonyl and your O minus that's formed, and then under acidic conditions you then have protonation to get your carboxylic acid. We can also have it being formed when we hydrolyze esters or nitriles. Okay, and we'll talk a bit more about the hydrolysis of esters in this topic. So we've got our ester, we've got a base hydrolysis. So hydrolysis is adding on hydrogens. So we've just swapped this R group for a hydrogen and we've made the R group into an alcohol. So hydrolysis is adding on a hydrogen to your molecule. Okay, and with the nitriles it's adding on our water. So we're adding on a bit more and it's under acidic conditions. So we'll talk a bit more about this reaction at a later stage. Okay, so carboxylic esters hydrolyze to the parent carboxylic acid and an alcohol. So they can occur two ways. So you can have it in acid with heat, or you can have it in base with heat. So when you have it in base, it's called saponification. Okay, so this example here is in base. So we've got our carbonyl and our OR group. We've got sodium hydroxide, and we're making the carboxylate anion. Okay, and we've got our OR being produced. So our alcohol. So what you could do here is then distill off your methanol and acidify this to get your charged species into the carboxylic acid form, so with a carbonyl with an OH. Okay. So saponification is the Latin word for soap, and it was originally made from animal fat. And we'll talk a little bit more about soaps in the next couple of slides. So the mechanisms for saponification, so again we're looking at the base hydrolysis of an ester, is when you have your base, so your OH minus, attack your carbonyl carbon, and then again your electrons bump up onto the carbonyl oxygen to get that negative charge. We then have them kick back down and kick out your OR group. Okay. Once your OR group is dissociated, it then comes back and deprotonates that carboxylic acid to make the carboxylate anion. Okay, so it proceeds via the tetrahedral intermediate that we have here. So esters and esterification. So condensation reactions are important in a biological context, and we'll talk a little bit more about this with polymers. So they undergo acid catalyzed reactions with alcohols to form esters. So our carboxylic acids form esters under acidic conditions with alcohols, and this is our Fissure Esterification. So we've got our acetic acid, for example, and we've got our ethanol, so this OH should be attached to this carbon chain here. And under acidic conditions, we have our ethyl adding on to our carboxylate, and we have H2O being formed. So the mechanism for this one is a little bit more detailed. Okay, so starting with our carboxylic acid, we need to activate our carboxylic acid so it's able to accept the alcohol. So this is done by the addition of a proton onto the non-protonated oxygen, so our carbonyl oxygen. So once this is protonated, we then get the positive charge. This positive charge needs to be quenched, so it drives the reaction by making the acceptance of the lone pair from this alcohol favourable. Okay, so accepting these lone pair of electrons and then losing the bonding electrons to quench this positive charge. So we have this tetrahedral intermediate again. So we've got a positive charge on this oxygen from the alcohol now, so we have a proton transfer. So the proton transfers from the OR to the OH, making the oxonium ion, so the water molecule that's then detached. Okay, so the lone pair kicks back in to kick that out, and then we get our positive charge again. So it's kind of what we started with, but now we have our OR attached. And then we have deprotonation, and we have our ester being formed. Okay, so let's have a go at this concept check. So name the following esters and indicate the products of reaction with hydroxide. So let's have a look here. So we have our carbonyl, our O, our R. So our R group is meth, eth, okay? And we have a phenyl. So we have ethyl, benzenoate. So ethyl benzoate. Reacting that with base, then we would have the cleavage of it, and we would get our O minus, and then our acid would be CH2CH3, so the CH2CH3 with the OH. Okay, so our next one here, we have, this is a phenyl, okay, and we have 1, 2, 3, 4, so it's benz. So it's phenyl butanoate. With our base, we're going to have the benzene ring come off with an alcohol, so we'll have benz alcohol as a product, and then we would have the O minus. So lipids are a structurally diverse range of naturally occurring substances which share the physical characteristics of being lipophilic, so non-polar, and are broadly characterized into two groups. So they're simple or complex. So the simple are monomeric units that are not easily hydrolyzed, and their complex ones can be broken down using hydrolysis. So the complex lipids are esters of long-chain carboxylic acids, and they are called fatty acids. So many of these compounds are amphithetic, having both polar and non-polar components. So let's have a look here. So we've got our free fatty acid. It's our carboxylate on one end, and we've got our long aliphatic chain, a non-polar chain coming off it. When we have it with glycerol and react those together, we make ester linkages, and glycerol, having the 3 OHs, will attach to 3 fatty acids. So this is our complex lipids, and this is our simple lipids. So when they're bound here, it's a good way of storing the fatty acids, and it also makes them less polar and less likely to hydrogen bond. Okay, so let's generally have a look at lipids, just to give you some background before you go into your biochem subject. So when we have our lipids, we have our long hydrocarbon tail, and we have our polar carboxylate or ionic head. Okay, so we've got a real dense electron population here, and we don't really have much going on down the chain. Okay, so depending on the environment that you're in, the lipids will act in different ways. So if you are in an aqueous environment, then the polar head groups will want to be around the water, so they all coordinate on the outside, and then all the hydrophobic tails coordinate on the inside, so we get a micelle. Okay. You can get liposomes, and you can get bilayer sheets, depending on the environment that they're in. So depending if you want the hydrocarbons out or the ionic polar groups facing out. So the cleaning power of soaps is due to their ability to act as emulsifying agents. So an emulsifying agent is a compound that sits between the interface of hydrophobic and hydrophilic. So it allows the hydrophobic liquid to be dispersed in microscopic droplets. So amphithetic molecules are essential in nature for forming semi-permeable membranes, allowing for controlled entry-exit of compounds. So membranes allow compartmentalization in living systems within cells, as well as form the cellular membrane. So the polar ends can interact with water, and the non-polar ends can interact with lipids. Okay, so for cells which have aqueous environments inside and outside, a lipid bilayer is needed. Okay, so we can have polar on the outside and polar on the inside. For my cell particles, only a monolayer is required since the interior is all lipid. Okay, so here are some common structures of your fatty acids which you'll learn about in biochem. So you can have your real linear fatty acids, but also there are ones that have kinks in them. So you can have one kink or two kinks or even a couple of kinks in them. And again, you'll talk about these in biochem, and you'll learn about the importance of having fatty acids with kinks in them versus fatty acids with no kinks in them. So let's have a talk about soap scum. So soap scum is an insoluble film that forms generally on hard surfaces. So how is it produced? So it's a reaction with your fatty acids and your calcium, magnesium or iron, so your hard water cations. Okay, so this goes back to your solubility rules as to why this occurs. So calcium salts are insoluble, so when you have your fatty acid, which is a sodium salt, reacting with calcium, then it forms an insoluble layer, so a scum. Okay, so it precipitates out. So how can we reduce the build-up of soap scum? So you could switch to more modern soaps and body washes. Okay, so generally our liquid ones, and they use your sulfonates. Okay, so these are sodium salts, and they do not form insoluble salts when they're reacted with calcium. Okay, so sodium lauryl sulfate is an example, and if you read into too much about soaps, then you'll realize that there's a lot of people that don't like your sulfate soaps, and they try and go more natural, but that's a whole area in itself. Okay, so let's talk about the reactivity of carboxylic acids derivatives. So the ones we're talking about are esters, acid chlorides, and acid anhydrides. So let's start with nucleophilic addition. So a refresher. So we've talked about aldehydes and ketones and nucleophilic addition. So we had our nucleophile attack our carbonyl carbon, and then we had the bonding electrons kick up onto the oxygen to get our alkoxide ion intermediate, and then it was protonated in an acidic environment and we got the alcohol. So we lost our carbonyl in the formation with our nucleophilic addition. So what we're going to talk about now is our last type of reaction, which is nucleophilic acetyl substitution. So nucleophilic acetyl substitution. So carboxylic acid derivative here. Okay, so we have our nucleophile attack our carbonyl carbon. Again, we have our alkoxide ion intermediate, but this time the lone pair of electrons kicks back in to make our carbonyl again, and we have a leaving group. So this Y group leaves. So what affects the reactivity is the substituent, so this Y group that's attached to the carbonyl. So this Y group, if it is electron donating, so pushing electrons to this carbonyl carbon, then it's going to be less reactive, and if it's pulling electrons away from this carbonyl carbon, then it's going to be more reactive. So let's think about this. So the carbonyl carbon, we want it to be really positive for that negatively charged nucleophile to come in and attack it. So the more positive we can make this, the more reactive it will be. So if we have a group here that donates electrons into this carbon, it's going to be less positive because it's accepting some of those electrons. So if it's less positive, it's less reactive. if the electrons are being pulled away from this carbonyl carbon, it's going to be making it more positive, so that it will be more able to accept that nucleophile that's coming in. So another thing to think about when we're talking about our reactivity is the leaving group. So how good is this Y at leaving? So it needs to be a good leaving group because it's got to leave, and we're going to make this carbonyl again. Okay, so again, this is our general kind of reaction that we're going for. So these are our substituents that we're talking about that are attached. So these are the substituents we're talking about that are attached to our carbonyls. So we've got our chlorine, we've got our anhydride, we've got our thiol, we've got our esters, so our thioesters, our esters, our carboxylic acids, our amides, and our carboxylate. So remember, your amides lone pair on this nitrogen. So that lone pair of electrons is really close to this carbon. So it's going to be pushing them into that carbon. So it's going to be decreasing that positive feeling of that carbon. So it's going to be less reactive. Our carboxylate is going to be very unreactive because it's got that delocalization of those electrons all around here. Our carboxylic acid, so thinking about the carboxylic acid, we've got two lone pairs on this oxygen, okay, and it's going to be donating them in towards this carbon. So similar to the carboxylate anion, you've got the stabilization of that. Esters are similar to your carboxylic acid. Your sulfur instead of your oxygen, so your sulfur again acts in a similar way, but it's less donating. Okay. Our anhydride, okay, so we've got that oxygen being shared over the two carbonyls, so there's less donation towards each carbonyl. And you've got your acid chloride, which is your chlorine, which doesn't actually donate any electrons onto your carbonyl. So your halogens act in a very kind of different way. So that's your more reactive. So your halogens are happy to have those electrons on itself. It's not going to be trying to push them onto that carbonyl. So this is our most reactive, and this is our least reactive. So another thing to think about is the resonance of the derivatives. So we've talked about the first two before, okay? So we've got our Z, which is our substituent that's attached. We can have it so there's a single bond to that substituent with a carbonyl, or we can have a negative oxalate, or we can have a negative on the oxygen and a positive on this carbon. Okay, so they're pretty common. But what we can also find is that then we can have the donation of the lone pair of electrons if Z has lone pair of electrons like it does in nitrogen, and we can get another one. Okay, so we will have three different resonance structures, so it's very stable and it destabilizes the reactivity of that carbonyl carbon. Okay, so it makes it less delta positive, and it's a stable molecule because there's more resonance structures of it, so it's less likely to be reactive. Okay, so the more electronegative Z is, the more it destabilizes this formation here. Okay, and the more likely it is to only have two resonance structures, therefore it's able to react more. Okay, so that's another kind of justification that you can think about when you talk about your reactivity, but the easiest way to think of it is to just think of what we talked about here. So how likely is that carbonyl carbon to be positive? So let's look at the substituent effects of derivatives. So if we have a chlorine, so a carbonyl with a chlorine attached to it, It's a withdrawing group, so it's what we call inductive, which we'll talk a bit more about next week. And it's a very good leaving group, so it's the most reactive. Our anhydride is weakly donating, and it's a good leaving group. Our thioester is donating, and it's a moderate leaving group. Our ester is strongly donating, same with our carboxylic acid, strongly donating, and they're equal fourth position. Our amide is strongly donating, so very strongly donating because it's pushing in that lone pair. And our carboxylate is a carboxylate anion, so it's very, very, very donating, and it's a very bad leaving group. Okay, so another thing we can think about is that can influence the reactivity is the carbonyl. So the more hindered the carbonyl, the less likely it is to react, because it can't have that nucleophile come in. So the more unhindered it is, the quicker the reaction will occur. Okay, so looking here, we have our carbonyl with the carbon and hydrogens coming off it. So there's quite a lot of room for a nucleophile to attack that carbonyl carbon. As we start increasing the bulk around that carbon that's attached to it, we have a decrease in our reactivity. Again, the more delta positive this carbonyl carbon is, the more likely it is to accept a nucleophile, so negatively charged species coming in. So looking at these electron density graphs here, so we've got our nitrogen, okay, and we've got our carbonyl carbon in the center here, and you can see there's lots of red here, and there's a little bit of blue. So blue is positive, red is negative on this diagram here. Okay, so electron rich and electron poor. So we've got electron poor around here, and then electron rich around the carbonyl, so it's going to be less reactive. Then as we decrease the negative, so our electrons around this center part, you can see it's decreasing, we're actually getting more of a reaction. So what happens if you have a less reactive system, so a molecule that doesn't react as well? So a less reactive system, you may have a nucleophile that's neutral, or you may have a less reactive electrophile. Okay, so your esters and your amides, remember, have low reactivity. Okay, so we can activate the nucleophile. So if a base is used, then this can activate the nucleophile by deprotonation, or we can activate the electrophile. So what we can do is activate that carbonyl oxygen by protonating it and putting in a system where it's activated, and it's going to make that delta positive bigger on that carbonyl carbon, so a nucleophile is more likely to get into it. Okay, so how are we going to activate the molecule? We're going to protonate our oxygen to make an OH that's positively charged. So when we have a nucleophile come and attack our carbonyl carbon, we're going to have a favorable reaction because we're going to be quenching this positive charge. So that oxygen doesn't really want to hold that positive charge. So by making it a positive oxygen, we can drive the reaction to occur better. So as the nucleophile comes in, we lose this positive charge and we just get our alcohol. Okay, our nucleophile, then we've got our methyl and our leaving group, and then our alcohol will kick back the electrons and kick out the leaving group, so you'll get that carbonyl, and then you have to have some sort of base around to deprotonate the carbonyl back to the carbonyl. So let's have a look at the summary of reactions and the derivatives. Okay, so how do we make a carboxylic acid into an acid chloride? We can thionyl chloride. Okay, so it just shows you here the sort of reactions that can occur. And these ones that we will be focusing on are on your extra sheet. Okay, so let's have a go at the concept check. So suggest plausible reagents for the transformations shown below. Okay, so we're going from a aldehyde to a carboxylic acid, so we're going to need a strong oxidizing agent, potassium permanganate. Here we've got two CH3, so again strong oxidizing agent, potassium permanganate. Okay, so let's have a go at these Grignard reactions. So we've got the Grignard reagent with a phenyl, which is a benzene ring with magnesium bromide. So phenyl with magnesium bromide, we have one equivalent, so it's going to react 1 to 1. So remember, this is essentially a benzene with a negative charge, which will come in and attack this carbonyl carbon. We will then have the formation of the O-. Okay, and the elimination of that OCH3. So we would get this product here. With this one here, we have a similar reaction attacking that carbonyl carbon and this side being eliminated. So we will get this product here. So condensation polymerization is the last thing we're going to talk about for this topic. So it's step growth polymerization. It employs difunctional molecules as monomers, and each new bond creates a separate step. So examples of these are polyesters, nylon, polyamides. Okay, so polyesters, for example, if you have diacid chloride or diester and a diol. So for example, we have a diester, so two esters, and we have a dialcohol, so a diol, so dimethyl esters, and we have dialcohol. When they react, we get our ester linkage, so we have the alcohol forming an ester with a carbonyl, and then we have our benzene in the middle, and then our carbonyl to the other side of the alcohol, and it keeps going on. So N is the number of repeating units that we have there. So there are some other ones that you may come across. So nylon 6,6 is one that we used to do in this course, which has now been removed. So you've got your polyamides, so your adipic acid and your hexadiamine. So you've got your diamine, you've got your adipic acid, and you're going to make a amide linkage. So thank you very much for listening to the lecture, and I appreciate you taking the time to refresh by looking through these recordings. They are not a replacement for the lecture. I talk about far more things in the lecture, and I do stuff on the whiteboard. But this is a summary of me going through the lecture slides to try and help as a learning resource for refreshing afterwards. So again, thank you very much, and